Oh, no, what? Oh, okay. Just a false alarm, they call that. All right, example 2. So we set it up. We're trying to find the area under the graph of x squared from 0 to 1. And the reason that it's kind of problematic is because there is no formula for it, right? You can do approximations, we said, with triangles and so on and so forth. But we're using rectangles, and it told us to use 4 with equal width. So from 0 to 1, the first thing we did is we found our delta x, b minus a over n. 1 minus 0 gives us a span of 1 unit. And to fit 4 things equally in there, they each have to be 1/4 wide. So then we went through and we drew the partitions, and we marked our x values, 1/4, 1/2, 3/4, 1. So I'm going to get rid of these little braces down here. And now we're ready to go. So on part A, it says to approximate the area using rectangles with left endpoints for the height. So we call that L sub 4. That means left endpoints with 4 subintervals. And here's what you're going to say. So you'll write it like this. The area of the region, squiggles, all right? Squiggles means approximation. Anytime it says to estimate or approximate, you got to have squiggles. All right, so with the left endpoints, if you want to draw it, I think we kind of did this yesterday. The first height is 0. The second height is the function value at a fourth. The next height is the function at a half. And then the final height is the function value at 3/4. So I'll go ahead and set it up rectangle by rectangle for this case, and then I'll show you how we can expedite that again. So here we go. The first rectangle is going to be the height, which is f of 0, times the width, which is 1/4. Plus, the next rectangle has a height of f of 1/4 times the width of 1/4. Plus, the next rectangle has a height of f of a half. Yeah, I said that. I will. I'm going to do this one more time, I said, and then we're going to get to the expedited version. Yes. You already know the secret, so I'm trying to show others the pattern or the secret. Times the 1/4. Okay, so as we saw up above when we were developing the idea using variables, we can see that down here again, if your delta x is something you're finding and it's a uniform width, it should be the width in every single term. So you can expedite these calculations if you want by just putting your delta x or factoring it out in front. And then all you have to do is, in this case, for the left endpoint, add up the first 4 y values. Now, when you put it at f of 0, f of 1/2, that's fine. The function's name is f of x. Or actually, it wasn't named f of x, so you would want to call it that. You can actually forego that step as well. You don't have to say f of 0. You can actually show the y value when you're plugging it in. So that would be 0 squared plus 1/4 squared plus 1/2 squared plus 3/4 squared. And if this were a free response, would you be done right there? You would be, yeah. It does 2 things. It indicates your method because the values that you're squaring show up here in your diagram. And then the 1/4 is your delta x up front. So this would be a 2-for-1. This would get a check for the method and a check because it's a numeric answer. But on a multiple choice, of course, that would not be an answer choice. That's too much typing. So let's go ahead and simplify it, knowing when to stop and then knowing how to keep going. So we get a 1/16 plus a 1/4 plus a 9/16. So if I put those all together, that's how many 16ths? Well, the middle one is 4/16. So that's going to be a 9 plus 1 plus 4, which should be 14/16. Yeah. And that simplifies down to 1/4 of 7/8, which simplifies to 7/32. Now, sometimes you might be able to determine if your approximation is an under or an over approximation. When in doubt, draw it out, okay, and you can clearly tell. They're not going to ask you if it's something like this. If there are some times where you're getting too much and sometimes you're getting too little, it's hard to know if your approximation is an over or an under. But in this case, it's indubitably going to be a what? Under approximation. When your function is monotonic increasing, whether it's concave up or concave down, turns out the left endpoint method always gives you an under approximation. Always. So we'll say that this one is like mama bear's area approximation. Too small. Okay. Now let's do the same thing, but with right endpoint methods. So I'm just going to come over here and get rid of these little purple horizontal lines. And now we're going to go with the right endpoint. So it's kind of nice to visualize it, because then you can answer that question, is it too big or too small? Or is it the Goldilocks just right? They call it the Goldilocks, but it's really the baby bear. Okay, so now there's the right endpoint. So here we go. Let's go straight to the expedited version. Using the right endpoints, we're going to put the area, squiggles, is approximated by 1/4. But now we're going to add up the last 4 y values. So f of 1/4, f of a half, f of 3/4, and f of 1. So we skip the first point for the right endpoint, and we use the last 4. Whereas for the left endpoint, we left justify it, and we use the first 4, not the last 1. So this should just be 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. And that right there, if you just do that and nothing else on a free response, with the squiggles there, that's a 2 for 1. That's check for the method. And again, to indicate the method, you're going to have to either show f of 1/4, f of a half, or you show the values that you've created on your graph, you show what you're doing with them in your calculation. And then, of course, because that's numeric, you're essentially done. So let's go ahead and compute this to see what it comes out to be so we can compare. You get 1/16 plus, that's 1/4, which is 4/16. So I'm already getting a common denominator. 9/16 plus 1, which is 16/16, right? So that turns out to be a fourth of, we're going to get 20 plus 10 is 30/16. Did I do that right? I did that fast. 10, yeah, it looks right. So that's a fourth of, let's see, 30/16 simplifies to 15/8. And that comes out to be 15 30-seconds. Now, based upon the picture, because it's monotonic increasing, your right endpoints, whether it's concave up or down, your right endpoints should always give you a what? An over approximation. So this would be the Papa Bear area approximation. Too large, not small. Too large. We use large instead of big. Large is a big word for big. Okay, now we're going to use the rectangles using the midpoint. This is my least favorite, but don't let my opinion of it jade your opinion of it. Here's the midpoint. We got to find new x values. That's why I kind of, groan a little bit, but that's going to be not a big deal. So here is the midpoint. Boom, there's the midpoint. So you go left and right, midpoint left and right, and finally midpoint left and right. Now I got to find those new x values. So what's the midpoint of 0 and a fourth? 1/8. Good. Yeah. So now you can either find the midpoint of all your intervals or just keep counting by an eighth, right? 1/8. The next stop is 2/8, which is 1/4. Then we got 3/8, 4/8, 5/8, 6/8, 7/8, 8/8 is 1. Good. There you go. Make it fun. Use inflection. And now we're ready to go. Here it is. The area is approximated by. Now, if you want, you could put m sub 4 in there before you go to your calculations. The area is approximated by m sub 4, which equals m for midpoint. We still have a uniform delta x, don't we? The width is still 1/4 all the way across. So because it's a common factor in every term, you can factor it out. And now you just add up the 4 midpoint y values, which you have them marked on there, your x values. So to apply the x squared function to them, it's just 1/8 squared plus 3/8 squared plus 5/8 squared plus the next one, the last one, is 7/8 squared. And that, again, is your 2 for 1. It indicates your method, tells exactly what you're doing, and it's a numeric answer. So let's see what this one simplifies down to. 1/4 of, that's 1/64 plus 3/64 squared, sorry, that's 9, plus 25/64 plus 49/64. So goodness, that is going to be, wow, calculator time. No, that's 50 plus 25, that's 75, plus 9, that should be 84/64. And then, of course, I'm going to simplify the 1/4 first. 84 divided by 4, that goes in nicely. That's 21/64. And does that even simplify then after that? I don't think so, right? So it's 21/64. So if you want to compare these, 7/32 is 14/64, and that's too small. And 15/32 is 30/64, and that one's too large. Do we know by looking at it if 21/64 is too big or too small? It's not immediately obvious, so you wouldn't be asked to say anything about that. But which one do you think should be more accurate, closer to the actual? Yeah, if you're just going to do one of them, the midpoint should be a little bit more accurate than either the left or the right by themselves. Do you think the midpoint is just the average of the left and right? You think so, Colin? Anyone want to jump on the Colin bandwagon? You got any room up there, Colin, on the bandwagon? Well, we can actually figure it out. Let's see. If the two left and right endpoints are 14 and 30/64, 30 plus 14 is, or what's halfway between, what's the distance between 14 and 30? 16, right? What's half of 16? 8. So add 8 to 14 or subtract 8 from 30, you get 22. So the average of L4 and R4 is 22/64. Is that the midpoint? No. So darn. But it's pretty close. Pretty close. Yeah, pretty close. All right, so the last one that we're going to do here is the trapezoid. Now, don't ask me how to trapezoid. I don't know if it's ever been done. You have to first build a zoid trap. T4. We're going to draw the picture. Draw the picture. And I can get rid of all these purple midpoints. They just obscure the graph now. So instead of using rectangles, we are now going to draw little secant lines. And remember that secant lines are always on the opposite side of the curve from tangent lines. So because this graph is concave up, not because it's increasing or decreasing, but because this graph is concave up, your secant lines are above the curve, and your little trapezoidal approximation should be a what? Should be a smidgen over, and should be pretty darn close, because we're getting just little tiny slivers more than we want. All right, so here is the trapezoidal. We did it up here. Remember the pattern for the trapezoidal with the uniform delta x is 1/2 delta x. The 1/2 comes from the formula for the trapezoids. The delta x is uniform, so we can pass it out. We're going to add up all the y values now. So with 4 subintervals, we actually have 5 y values, right? 1 on the end and the 3 in the middle. We're going to use all of them, and we're going to double only the ones on the interior. Now, because we're using an extra y value and we're doubling the other two, our sum is going to be probably a little bit bigger, maybe twice as big as the others. That's why the 1/2 is out front, to put it back down to size. So here's what we could do. Memorize this pattern. For the trapezoids, we'll say the area is approximated by T4, which equals 1/2 is part of the formula. Delta x is uniform. It's 1/4. We'll factor it out. And now all we got to do is add up all the y values, squaring the runs in the middle. So the first y value is 0. So it's 0 squared. Plus twice 1/4 squared. Plus twice 1/2 squared. Plus, we have one more in the middle, right, at 3/4. So plus twice 3/4 squared. And then finally, the last y value just gets used once, plus 1 squared. That is the pattern that you want to memorize for the trapezoidal approximation when you have a uniform delta x. 1/2 delta x plus add up all the y values and double the ones in the interior. All right, so now let's go ahead and simplify this. That gives you, that by the way is where you'd stop on a pre-response, sorry. So now you get a 1/8 and you're left with 1/16 times 2 is 1/8. Plus 1/2 squared is a 4th. A 4th times 2 is 2/4, which is a 1/2. Plus you're going to get 3/4 squared, which is 9/16 times 2 is 9/8. Plus 1 squared is 8/8. So if we get all of them in terms of 8s in there, let's see what we end up with. We end up with 1/2 is the same as 4/8, right? So we have 9 plus 1 is 10, and then 4 plus 8 is 12. So that gives you 22. 22 eighths, which when you multiply straight across gives you 22 64ths, which of course simplifies down to 11/32. But 22 64ths, haven't we seen that guy already? Yeah. When we were checking to see if the midpoint ended up being the average of the left and right, we stumbled across 22 64ths. Now we've got 22 64ths. Is that a coinkydink? No, it's not a coincidence. In fact, because you're doing it with lines, secant lines, even though the curve varies, when you do a line from one segment to the next, it's going to be the average y value is going to be the average of the leftmost y value and the rightmost y value, which are the left and right endpoints. So it turns out that the trapezoidal area you can always find by its own unique pattern, but it's also, we'll work backwards here, it's also always equal to the left endpoint and the right endpoint's average. You don't want to have to always do it that way because sometimes the question may just ask you, what's the trapezoidal approximation? And you don't want to have to find the left, and then find the right, and then average them together with the right notation. When you can go straight to the pattern of 1/2 delta x, add them all up, double the ones in the interior. Sometimes that's a little bit faster. But it does turn out to be the average of the two. Okay, so of these different calculations, which one is going to be the most accurate? Is that easy to tell? This is a little bit over. This is an over approximation. So we know it's got to be a little bit less than that. The midpoint was 21 64ths. That's a little bit less than 22 64ths. So maybe the midpoint is more accurate. But what if it was actually, 21.999 64ths? We don't really know if the midpoint of the trapezoidal, which one is more accurate. But those two by themselves should be more accurate than either the left or the right. All right, so now on part E, we're going to use your calculator's numerical integration capability. The way it computes these is by using the rectangular sums, but it uses a lot more rectangles than the 4. So it's kind of closer to what Skylar's program did. So here's how you would do it. There's two ways to actually do it. And if you just want to watch, if you have a calculator, you can play along, but I don't think it's worth running up here and grabbing one. So here's the two ways to do it. Number one, you could type your function in, y1. So that's x squared. Now let's go ahead and graph it in the same window that we were given. That's going to be from 0 to 1. I'll turn my x scale off. And our y scale is from 0 to 1 squared, which was also 1. And we'll keep that off. So if you hit graph, oops, I need to put my x-min at 0. There we go. Now we're looking at just a little piece of the graph. We want to find the area under this curve. From the graphing screen, if you go to your calculate menu, second trace, which one of those scrumptiously umptious looking menu options do you think we'll choose? Number 7, exactly. Because what we were doing is we were taking the product of y values, f of x, times little bitty delta x's, or in this case dx, and the s in front means add them all up, right? So we are going to choose 7. It's going to ask you now for your lower limit. That's your starting value on the left. That was x equals 0. So hit 0 and hit enter. Now your upper limit was what? 1. Yeah, 1. Now when you hit enter, be prepared to be wowed. Wow. It shaded it for you. Did you know your calculator can color? So you could kind of see the resolution pixels here. You could think of each vertical column of resolution as one little tiny rectangle. So you can kind of see it stepping up. But it uses enough rectangles that, at least to the number of decimals that it shows, it's actually correct to the actual. So for the answer down here, what is your calculator's area saying it is? Very good. Okay, yeah. 1 minus 2/3, right? 0.333333 is 0.4 or 1/3. There you go. So the area is equal to 1/3. That's the actual area. The actual area is 1/3. Sweet. So why did we do all this when we just had our calculator that could do it for us and give us a better answer? If you're on a deserted island and you have your calculator, but the batteries are dead, did you ever think about that? And you need to compute area approximations to get off the island. Like someone comes with a boat and like, I'm not letting you off unless you can approximate this or tell me what the area under the curve is. You would need to know this information. Okay? And you're not allowed to ask the guy rescuing if he has 4 AAA batteries so you can make your calculator work. We always like to walk through the footsteps of our mathematical forefathers so we can appreciate what they went through, and it also increases our level of understanding. But there is, soon to come, a very easy shortcut method for coming up with 1/3 on our own. And it does have something to do with the indefinite integral from 4.1. But I'm not going to give that away just yet. Just yet. All right. Any other questions or comments on this other than, wow? Why? Well, it's like Satchel Paige said. If you have to ask, you'll never know. Yeah, okay. Maybe that wasn't Satchel Paige. We'll just say it's a misattributed quote. It was somebody. They asked somebody what jazz music was, and he said, if you have to ask, you don't know. Satchel Paige was a baseball player, not a jazz musician. So anyway, get on that. All right. So anyway, here's the picture that we really don't have to look at anymore because we had Skylar's little Java applet. But if you take that same region and you use 10 rectangles, then the right endpoint is 0.385. If you increase the number of rectangles to 30, then the right endpoint is 0.3502, which is a little bit too big. If you use 50 rectangles, it's still too big, but by less, 0.343. After 50, it gets really, really hard to show the rectangle. So if you just go to tabular format, at 100 rectangles, the right endpoint is 0.338. At 1,000 rectangles, the right endpoint is 0.33383. And you can kind of see that as n gets bigger and bigger, the right endpoint, which is the Papa Bear approximation, too big, it gets smaller, approaching 0.33333. And the left endpoint, which is the Mama Bear version, too small, it actually increases, approaching 0.33333. And so there's the idea of the limit, as we said yesterday. So let's just say it again. The limit, as n goes to infinity, of your approximation methods, we'll just do it real informally here, of the approximate area, it's going to equal the actual area. And so this is the second half of the house of calculus. It's built on the idea of the limit again, and this is going to be known as definite integration as opposed to indefinite integration. All right, so again, I mentioned this guy. I don't think I mentioned this guy yesterday, but this was one of Gauss's prized students, Gauss being the second guy from the left on this wall here. This guy is a German, just like Gauss, Bernard Riemann. Okay, that's how you pronounce it. That's the German spelling, Riemann. That's how you pronounce it. So he's the guy that did the work on essentially, for the most part, taking the finite process, putting the limit in front, which is an infinite process, and going through the mathematics and turning it into what's going to be known as the definite integral. Okay, so just like the limit definition was what we did first for the derivative, and then we learned the shortcut rules, there is essentially a shortcut rule for computing areas under the curves. And because Riemann is the guy that did the legwork on the theory, we pretty much get rid of the word rectangle in our calculations, and anytime we use rectangles, we call those Riemann sums. Okay? So it's named after him. A Riemann sum is an approximation of an area of a region using rectangles. So it's real easy to remember. Riemann, rectangle. Neither one has a Z in it, right? So it makes it easy to remember. All right? They both start with R as well. That's another thing that might help you remember. So the instructions might just say approximate plus U, the area of the region using four Riemann sums of equal width. Okay? So like Riemann, oh yeah, there's no Z. That means rectangle. Now trapezoidal approximations, it's just going to say using trapezoids. Okay? But anyway, it's kind of interesting to notice the similarities here. The finite process of adding up all those areas uses the Greek letter sigma, which is the Greek letter S. And we're taking actual y values times thicknesses of x that are finite and measurable. But when you let n go to infinity, you turn it into not adding them all up from a to b finite. You get the sigma kind of straightening out into what's called the integral symbol, of course, but it looks like a letter S. And that's not by coincidence. It's because it's still a sum. So it's the infinite sum from, we read this on the bottom as, from A to B. The infinite sum from A to B of your function values times dx instead of delta x. Remember, dx is your infinitely small, non-measurable horizontal distance, right? So basically, delta x, as it approaches 0, it becomes dx. And what we get then is something that looks exactly like what we did in 4.1, except it has these intervals of integration on it, we call them. And when you see those, that's what makes it a definite integral. And when you evaluate this definite integral, you get a definite answer that represents the what? The area of the region. Yeah. Or in general, it's going to be known as the net accumulation. But right now, we're thinking about it in terms of areas. All right, so let's try it again here. Since we have this new notation now, we know what that means. So approximate this definite integral. We read that as the integral from 1 to 9 of the square root of x with respect to x. The integral from 1 to 9 of the square root of x with respect to x using 3 subintervals of equal width. All right, so let's draw the picture. The square root of x is our function. It's the integrand now. It looks like that. We're going from 1 to 9, not 0. So we'll start right here, call that 1, and I'll just call that 9. And I got to divide that into 3 pieces. So instead of bisecting it, you kind of have to draw 2 lines on the interior. Okay, so now we can find our delta x. Delta x, again, is b minus a over n. I'd write that out until you have it memorized. We're going from 1 to 9, so our total distance is 9 minus 1. It tells us to use 3 subintervals, so each one of them is going to be 8/3 in length. So for us, now we can go ahead and establish our stopping points. 1 is, of course, the first one. The next stopping point is 8/3 away, which would be what? 1 is the same as 3/3, right? So 3/3 plus 8/3 is 11/3, plus another 8/3 is 19/3, plus another 8/3 gives you 27/3, which is 9. So now we have our stopping values, and don't forget 0 is the first one over here. All right, so we can go now with Riemann sums. Now, we're not calling this area, we're calling it the definite integral. So instead of saying the area is approximated by, on each one of these, I'll just say the integral from 1 to 9 of the square root of x dx is approximated by. You'll see in the next section that the definite integral is not always going to give you area. Okay? But in this case, it is. And I'll explain the criteria for that later on. Okay, so now I'm going to put that's approximated by, since we're using left Riemann sums, that means rectangles, I'm going to call it L sub 3, because we're using 3 of them, and that's going to equal. Okay, now if you want to draw it, feel free. I'm not going to do it. Is our delta x uniform? Yeah, right, it's the standard width of 8/3, so we can factor it out. And now all we have to do, because it's left justified, is add up the first 3 y values. So that's going to be f of 0, f of 1. I'm sorry, why did I go all the way back to 0? I didn't shade it, and now I'm messing myself up. We're not starting at 0. Good thing we knew we were supposed to have 3 y values. So that doesn't hurt to shade it at least. We're not always starting at 0. Okay, so now that's a little bit better. All right, so we're starting at 1. So it should be f of 1, which is the square root of 1, plus f of 11/3, which is the square root of 11/3, plus f of 19/3, which is the square root of 19/3. So notice we're left justified. We didn't use the 9. We used the 1, the 11/3, and the 19/3. And that's your 2 for 1 again. The values that you're plugging into your function, 1, 11/3, and 19/3, I can see those up above. I know exactly what you're doing. You're plugging those into your function, and your delta x is out front because it's calculated over here. I know that that's 8/3. Now, I'm not going to even evaluate that. Okay, we're just going to leave it like that. Now, is that going to be too big or too small? Is it hard to tell? Yeah, well, what if it were concave up? Would it still be too big? If it were concave up, it would look like that. We just kind of did that up here, didn't we? Was the left endpoint too big or too small? It was too small. Yeah. So as it turns out, when you're doing Riemann sums, it doesn't matter on concavity at all. It only matters if it's increasing or decreasing. When in doubt, draw it out. Because this function is increasing, the left endpoint Riemann sum is an under approximation. So I'll say that this is an under approximation. Under approximation since, or because, the square root of x, y equals the square root of x, is increasing on the interval from 1 to 9. Or I should say the open interval. Again, Riemann sums only depend on whether it's monotonic increase or monotonic decreasing. It's only the trapezoid that depends on the concavity. All right, the right Riemann sums. Again, we're not going to even draw it. We're going to go straight to the calculations. So I paste this. The integral is approximated by, if you want to get a different name, you can call it r sub 3, which now equals. 8/3 is still our delta x. It's still uniform. But now we're going to right justify it. So we're going to skip the 1 and use the y values at the last 3. So it's going to be 11/3, the function value, which is the square root of 11/3, plus the square root of 19/3, plus the square root of 9. And there it is. Correct. That's a good point. If you want this to count for your method as well as your numeric answer on a free response, you have to call that the square root of 9. You can't call it 3. Because if a 3 shows up in that last term, the graders and I will be like, where are you getting 3 from? Did you bring that one with you? But if you put the square root of 9, we're like, there you go. 9 is the right endpoint, and it's under the radical, which is the function. So you got to be tempted, you got to avoid the temptation of simplifying. If you want to indicate your method and have it count as your numeric answer, you got to have the numbers appear from your chart or your table or your graph in your calculations. All right, will this be too big or too small? Over or an under approximation? Over, yeah. So when in doubt, again, just draw it out. Right endpoint. Ooh, it's not with a highlighter, though. Right endpoint, right endpoint, right endpoint. So kind of for the same reason, this will be an over approximation. And the same reason would be since that is increasing, monotonic, you could say, strictly increasing on the interval from 1 to 9. All right, and notice I didn't ask for the midpoints. That doesn't show up that often. So now for the trapezoids. Since you have the left and right Riemann sums, you're welcome to write all of that plus all of that divided by 2, or you can just go straight to its own pattern, which you should know. You should know how to do that. So let's review that. We'll call this T sub 3. There's always a 1/2 in front for the trapezoid. If your delta x is uniform, which it is, you can factor it out. And now with 3 subintervals, you're going to have 4 terms. The trapezoidal always has 1 extra term than the number of partitions. So you're going to use all of them. So the first one is the square root of 1, which is singled. Now everything on the interior, namely the 2, 11/3 and 19/3, they get used twice. So plus twice the square root of 11/3, plus twice the square root of 19/3, and then finally plus the square root of 9. Double the interior, however many there are. Just remember your first and your last are exterior walls. They're only used once. Everything else on the interior is a joint wall between the interval on the left and right. So they get doubled. And there's your 2 for 1. Indicates your method. It's a numeric answer. Cool. So actually figuring out what that is at this point is not as important as knowing how to set it up, because of course we have the calculator to give us a better approximation with less work, and soon enough we'll know the shortcut rule ourselves so we can get the exact answer. Now, is this an over or an under approximation? This one doesn't care if it's increasing or decreasing because these are little secant lines. It only cares if it's concave up or concave down. Secant lines are always on the opposite side of the curve from tangent lines. So if you just draw it, when in doubt, draw it, you notice you're not going to be getting enough. You're going to be missing these little slivers. So that should be a what? Under approximation. But here's the reason. This is an under approximation. You'll say not since the function y equals the square root of x is increasing, but since the square root of x is concave down on the interval from 1 to 9. All right, so if you were really, really curious and you had time and you had a calculator, you can do it from the graphing screen. Now, I did tell you there was 2 ways to do it. So let's go ahead and do this one the other way. The other way to do it without graphing it is you could still put it in to a y. I'll put mine into y2. But if you're only going to use it once, you could just type it into the home screen, which is where we're going to do the other calculation. So here we go to the home screen. And now to compute these definite integrals, as they're going to be called, from the home screen, you hit Math. And remember, Math 8 was the derivative. Look at Math 9. It says f and int. That's the most extreme type of int out there, the f and int. What do you think that stands for? Not finite, function integration. Yeah, function integration. So Math 8 is the derivative. Math 9 is the integral. And if you're in Math Print, it actually gives you a nice little definite integral template. You can also get that by hitting alpha window. There's a shortcut to it. It's number 4. Okay, so if you have the new Math Print, you can get to the shortcut. I like just saying Math 8 and Math 9. So anyway, let's go ahead and fill in the blanks here. That's going to be a 1. That's going to be a 9. You can either type in the square root of x right here, or if it's an ugly equation that you don't want to have to type in again, alpha trace, remember, gives you a shortcut to your y's. We put ours in y2, and then with respect to x. So this is how we're going to be finding definite integrals on our calculator. We're not going to do it graphically because we tend to kind of get distracted when it shades it. Ooh, and then you forget what you're doing. But if you do it on the home screen, you're not tempted by the pretty graph. You get 17.33333, which of course you know the old math enter trick. Guess what the actual area is? The actual area is 52/3. That's not an approximation anymore. The calculator uses so many rectangles in its partitioning that it effectively gives you the right answer. Sometimes it doesn't get it all the way down to the end. It'd be like 17.3333332. And then you have to be like, I know what you mean. I know what you mean. All right, so good so far, so good. How are we doing on time? We still got 13 days till Christmas. Plenty of time. All right. This one says sometimes we can actually use known geometric formulas to come up with actual values for our definite integrals without having to approximate it. Case in point, example 4. It says to evaluate this definite integral from 0 to 4 of 2x with respect to x by expressing it as an area. All right, so the function that we're trying to find the integral of is 2x. And, of course, we know what that looks like, right? That's a line. It passes through the origin. It goes up 2 over 1, up 2 over 1, up 2 over 1. So it looks something like that. We're interested in finding the integral from 0, which is right here, to 4, which is conveniently right here. So bounded by the x-axis, we want to know what this is. So it does turn out to be the area. And right now, that's all you know about the definite integral. It does give you the area. Do we need to partition this up into Riemann rectangles to get the approximate value? No, because it itself is just a what angle? A triangle. Good. Yeah, very good. So here we go. We'll say that the integral from 0 to 4 of 2x dx, not squiggles, but what? Equals, right. And then the area of a triangular triangle is 1/2 the base, which from 0 to 4 is 4, times the height, which is, Plug it in where? Oh, the 2x, good idea. 4 times 2 is 8. All right, that was easy. So there's the height. Now you stop there on a free response, right, because you don't want to mess up a good thing. You keep going and you get 4 times 4 is 16, or 2 times 8 is 16, or 1/2 times 4 times 8 is, it's all 16. So 16 is the actual value. You think your calculator knows that? I hope so. Let's verify on the calculator. We know we're right. Let's see how good the calculator is. Math 9, we're going from 0 to 4, toggle up, of the function 2x. So in this case, I'm not recalling it from y1. I'm just typing it in with respect to x, and it better give us 16. Ah, it knows. Way to go, calculator. Money well spent. Twice for some. You never did find your first one, did you, Tyler? Okay. It's out there somewhere, helping a math student along their journey. All right. So since we've been finding these definite integrals now, which is what we call the integral with the little intervals of integration on it, and we've been calling them area, I think we should actually formally define what an area is in relation to the definite integral, okay? So here is what is in the box. It says if y equals f of x is non-negative. What does that mean? Positive, or could be 0. If the function is non-negative and integrable, what does that mean? Integrable means you are able to take the integral of, literally, that's what it means. That means you are able to find what we've been doing, the area under the curve. We'll kind of tie it to something else later on, namely continuity. So if the function is essentially non-negative over a closed interval, then the area under the curve bounded by the x-axis from A to B is defined to be this. A for area is the definite integral. Again, we read that from A to B of f of x dx. So everything we've done so far has qualified. We've had pieces of graph that have been non-negative. They've either been above the x-axis or on the x-axis. When you integrate then from left to right, that's important too, from left A to right B, your value of your integral is going to be a positive number, and that positive number will definitely give you the area. The second part, what if y equals f of x is non-positive or negative over that interval? If you were to look at this function right here, from A to B, if you were to use Riemann sums, what sign would you get on the definite integral? You would get a negative, right? Because if you just partition it up, notice your delta x is a positive number. But because you're using function values for the height, and your function values are negative, you're going to get a negative value. Could you then call that negative number the area of the region? You could, but people would laugh at you, right? You ever go into Sherwin-Williams and say, hey, I got to paint my house. I need to get some paint. What's the square footage? Negative 20. Oh, I guess we owe you money then, sir. Right? That doesn't make any sense. Negative area. Area has to be what? Positive. So, what could you do then if it was entirely negative, and let's say you came up with that to be negative 4, and you wanted to know the area? Just take the absolute value of it, make it positive. So, bless you. Here's what it says. If f of x is entirely negative on the interval from A to B, then the area under the curve from A to B is the opposite of the definite integral from A to B. In other words, the magnitude of your definite integral is going to be the area. That's if it's entirely negative. The question then becomes, what if you are integrating over a region that has both positive and negative values? If you want the area, you got to find them separately and add them together. Very good. Because what the definite integral gives you is not always the area. Okay? As we just saw, if you have negative y values, it's not the area. But it gives you something called the net accumulation. In other words, the sign matters. If you're going from left to right and you have a positive region, you're gaining things. And when it's below the x-axis, it's negative, you're losing things. So if you just took the integral of a function from left to right, sign matters. So let's look at this curve right here. If we look at it from left to right, if you took the integral from -5 to -2, that's going to give you a positive number because your y values are positive. But if you integrate from -2 to 3, you're going to get a negative number because your y values are negative. If you then integrated from 3 to 5, you're back above the x-axis, you're going to get a positive number. So if you just integrated, let's call this region A for the area, call this area region B, call this C. What if I knew the actual areas, okay, of these three regions? When you take the integral then, all the way from left, -5 to right, +5 of this function, you're going to get a positive A for the first interval. You're going to get minus the area of the region for that one, and you're going to get plus C again for that one. So this does not give you the area. If you wanted to paint this region and you're subtracting this middle region, you're not going to have enough paint, right? So the definite integral can be used certainly to find areas, right? As Noah just said, if you wanted the area of the region from -2 to 3, just integrate it from -2 to 3 and then change the sign. And now you'll have the area. So you can use the definite integral to find area as long as you know where it's positive and where it's negative. But if you just integrate straight across on a region that has both positive and negative values, you're not going to be getting the area. You're going to be getting the net accumulation. Yes, Indy? When would you put it in absolute values? What is it? If you put, very good, if you put the entire function in absolute values first, now that transformation, remember, flips any negative values across. That is a good way to do it if you have a calculator. If you don't have a calculator, when you put absolute values around a function, you're going to see in the next section it makes it very, very hard to find the antiderivative. So we actually define that down here. Let's jump down there because that's where Indy took us. This is called the area under the region of a calculator theorem. And it says, if you are interested truly in finding the area and you have a calculator, then on the interval from A to B, the area is defined to be the integral from A to B of the absolute value of f of x. Your calculator can handle those calculations a lot easier. But for you to do it by hand, it's really hard if you have the absolute value in there. So we have a method by hand. If we're into the area and we don't have the calculator, we have to know then where the graph is positive and where the graph is negative. And we can integrate from left to right like normal if we're on positive land. But if we're in negative land, we need to be careful and change it to positive. Okay, so there's a manual way to do it. You just have to split it up and do them in pieces. All right, so that's if you integrate from left to right. That's chronological order if you want to think about it that way. What happens if you integrate it from right to left? Should be the opposite, right? If you watch a movie going forward, you're like, oh man, this is a story about a guy that gets rich. If you watch the movie in reverse, it's like, whoa, this is about a guy who gets poor, right? So whenever you go backwards from right to left, from greatest to least, you're telling the story in reverse chronological order. So let's go ahead and see what this movie's about. This guy earned something from -5 to 2. Oh, and then he lost it from -2 to 3, but he gained back a little bit from 3 to 5. Great movie. Let's watch the movie in reverse. Oh, he lost something from 5 to 3. You'll actually see him giving money back, right, in the movie. And then from 3 to -2, he's like gaining back what he lost in the movie going forward. And then from -2 to -5, he's losing money again. So that's very important. When you integrate from right to left, from greatest to least, everything is the opposite. Everything above is now negative and everything below is now positive. So that's kind of important. That gives you a different way to change the sign of the integral. If you wanted to know what the area of this region was, you could either do this. You could say the area is the integral from -2 to 3 of f of x dx, and then change its sign, right? We just said that in the box. Or we have another way now. Simply just integrate it from where to where?
Good morning, Unicorn.
3 to -2. If you integrate it in reverse order, it will make it positive as well. Let's pledge, everybody. United States of America, and to the republic for which it stands, one nation, under God, indivisible, liberty and justice for all. Honor the Texas flag. I pledge allegiance to the Texas, one state, under God, one and indivisible.
Please remain standing for the moment of silence.
Reflect upon this as you moment of silence. We'll stop right there for the day. This is important. If you ever flip the interval of integration, you put a negative out front. We'll pick up there tomorrow.